Okay, everybody, I apologize for that slight delay. I just didn't put the link in Canvas. I apologize for that. And anyway, okay, let's take a look at some of these things that we were looking at yesterday. So you guys notice that, we're going to start to transition. We're going to use these ideas. I'm going to give you guys a fact here. We're going to start to differentiate and integrate, but we're going to differentiate the natural log here, okay? We're going to see what this actually is equal to, that derivative here, okay? So we're going to start to do calculus now of log functions. And to start off, what we're going to need to do is know the definition of a log. And I think I gave it to you here. Yeah. So here's kind of what we start with in case you guys didn't know. Okay, let me kind of copy that. It's your log definition. Okay, so remember log base E, that's natural log, is that right? So we're going to say, okay, that's log base E. And we know that that's equivalent to e to the y equals x. So if I say to you guys, what we're going to now do with this definition here, we're going to differentiate because what they're saying is if you ever see a function like this, y is natural log of x, that's what they want you to use, that portion here. Okay, so we say, okay, let's differentiate e to the y now, which is e to the x. Now, of course, y here is a function of x, okay? So this y is a function of x. And what that means is we have to use on the left side, we're really having to do, oops, messed up, ladies and gentlemen. Sorry. G dx of x. Sorry about that. Differentiating both sides with respect to x. So this is really, again, implicit differentiation. So on the left side, of course, we have to use our chain rule. And you say, well, what is that going to be? Well, that's e to the y times y prime. Is that right? Because that's dy dx. And on the right side, the derivative of just x with respect to x is 1. Okay, so remember this, even though I put y prime, that's code for, dy dx. And we do like to use that notation because it's easier to write down. And so now what I'll do is I'll solve both sides for e to the y, okay? And then you already know what e to the y actually is. You say, well, what is e to the y anyway? Well, that's x, okay? So what I've showed here is that y prime is 1 over x, and that's actually what I've wanted to show here. Okay, so the derivative of natural log, ladies and gentlemen, is 1 over x. This is gold here, okay? All right, you guys okay with that? There's your derivative now. So differentiate natural log, and it's just simply 1 over x. Now, once you have that, you might say, well, what is this? We have the chain rule version. Chain rule is if I have to differentiate with respect to x, natural log of u. Where again, u is a function of x as well. So this is actually composition of functions. Yeah, I don't know why this is so slow, but anyway. And you say, well, what is that going to be? It's, remember, chain rule. So you have to differentiate u with respect to x. This is the chain part, okay? So, ladies and gentlemen, this is our gold here. This is chain rule. Chain rule, and then this is the what? The derivative formula here. All right, you guys okay with that? That's where we're headed. And then I'm going to have to say, by the way, because we're going to have to right now you might say, what about the integral formulas? So for integration, though, I'm going to have to do a note before I give you the integral formulas. I'm going to say this to you guys. Let's note the following. I'm going to let y be the natural log of the absolute value function. See, this is going to give us a more complete integral formula. Okay? And so if you ever remember how absolute value is defined, okay? That's the natural log of x when x is greater than 0. And that's the natural log of minus x when x is less than 0. Now you might say, what happens when it equals 0? This is not defined for 0. If you guys know, this function is not defined at 0. Okay, so if you say, what do you mean? Well, you can't plug 0 in there. Absolute value 0 is 0. Natural log of 0 is undefined. So anyway. Okay, so we're going to consider this function. It's a little bit more sophisticated. And then you remember what this actually means, right? This is going to imply that y prime now, right? If I differentiate this function here, y prime is just going to actually now be, the derivatives piecewise. d dx natural log of x, which is 1 over x, because we just seen that. And that's good for when x is going to be positive. And then if you said, well, what's this derivative of the natural log of minus x? Well, this is where I have to use what? Chain rule. That happens when x is negative here. So the denominator work here is not done because I now have to take the derivative of, by chain rule, negative x is negative 1. So so the moral of the story is going to be this. Right? Y prime is going to be, again, piecewise. 1 over x when x is positive, and it's also, again, 1 over x when x is negative here, ladies and gentlemen. And so what this means really is, and I guess you could say y or f does not matter, that the natural log function in absolute value implies that dy dx, or that derivative, is 1 over x, and x simply is not 0. So x can be positive, or x can be what? Negative. Okay? Now, you might say, why is that so important? Okay? It's important, and let me write it symbolically. That when you differentiate the natural log of the absolute value, that's 1 over x. X is not, 0. Now, that implies that if I integrate 1 over x dx, natural log absolute value of x plus c. Okay? So that's why I had to go through this function with the absolute values, because we have a more complete integral formula. Okay, so this is our integral formula here now. This is what we care about. And after you get an integral formula, you always get free of charge the u subversion. Okay, meaning if you have to integrate 1 over u du, that's the natural log absolute value of u plus c. Okay, so you have a nice u subversion as well. Okay. All right. Good, good, good. Double check here, ladies and gentlemen. So we got some nice things to do. So we got nice formulas. We can differentiate. We got derivative formulas. We got integral formulas. The rest now is to have some fun. Is that right? You say, what do you mean? Well, how do we apply it? That's what I mean. How do we apply these things? So, for example, the tried and true. Determine the what? Equation of the line. Tangent to the curve at some location P. So again, they're going to give you a function, and the function that they have here, we're going to start with natural log of what? X squared, and then that point P is at 1, 0. Okay, it's that tried and true equation of the line. And of course, the tangent to the curve part, that's the calculus part. Okay. All right, so remember this. You have what? The algebra. Y minus y1 is m times x minus what? X1. Here's your x and y. Okay, the one and only point. So you say, is that y minus 0 is m x minus 1? Yes, it is, but we need m tangent. M tangent, you guys know, what is M tangent, right? We have to find dy dx. So we differentiate with respect to x, natural log of x squared here. And that derivative is 1 over x squared, the derivative of x squared. Now, the derivative of x squared is the value, or is what? You guys know by power rule, isn't that 2x? Okay, you guys see how we're using this here? This is chain rule for this. So that'll be 2x over what? X squared, which is just 2 over x. Now, that's the derivative here. So we can say, okay, that's dy dx using the formulas that we derived. But we have to evaluate that at what? 1, 0. Is that right? So for m tangent, evaluating that at 1, 0, that's the point. That's really x is 1. So that's your m tangent, again, all the way from calculus 1. So that'll be 2 over 1, better known as what? S2. Okay, so my m tangent is the value 2. That is what goes where? Right in here. All right, so you got m tangent. So remember, do the rest. Y minus 0, 2x minus 2. And ladies and gentlemen, you're done. This is the equation of the line, tangent to the curve at the location 1, 0. It's 2x minus 2. And so let's go out to Desmos, if we can find Desmos. So, okay, Desmos, here you go. Y is natural log. Y equals 2x minus 2. Okay. 1 comma 0. Label. And again, I'm going to change the color. How's that? Bless you. So take a look, ladies and gentlemen. What do you guys have there? The curve in orange is the curve, natural log of x squared. Okay. The 0.10 is green on the curve. Y is 2x minus 2. Isn't that tangent at the location? And blue. Okay. So there you go. An application of all this here. Okay. All right. You guys okay with that? And then let me do another one for you guys. They're going to say determine again. Determine the intervals of what? Increasing and what? Decreasing. And the curve now, y is maybe natural log x over x. I just want you guys to know the domain here is that x is what? X has to be positive, right? Because the natural log function is not defined for negative values of x, nor is it defined at 0, and especially if it's in the denominator. And I'm going to go again to Desmos and say Desmos where are you again? Natural log of x, okay, divided by x. Okay, so I want to get rid of all this other stuff. And take a look at what's happening with this curve, by the way. You guys know what I'm saying? Sounds like that looks like that's a special point. So just looking at the graph, it looks like your function is what? Increasing what? Everywhere. Is that true? No, it's not. I'm sorry. It's not increasing everywhere. Your function's increasing. It reaches a point, and then it decreases. Okay? So let's do the analysis. Let's do the calculus. So what do we have to do when they want to find intervals of increasing, decreasing? What was that code for again? It's sign analysis on what? Y prime. So, okay. So y prime then is the derivative with respect to x of what? Natural log of x over x. So if I ask you guys, what rule do you guys use here to get the derivative, right? What is that going to be? It's quotient rule. So I have x squared, x, differentiate natural log x, right? Minus natural log x, you differentiate x. This is quotient rule, ladies and gentlemen, quotient rule. And what's the derivative of natural log of x? That's going to be what? Okay, what's the derivative of x? 1. Y prime x times 1 over x minus natural log x over x squared. And this is now going to give me, ladies and gentlemen, 1 minus natural log x over my x squared. So remember sign analysis. You go, what's sign analysis? Well, a couple of things. If you had to do sign analysis just by looking at that function, right? Here's what people might do. They do this. Remember, because the process of sign analysis, when you have a rational function, you let the numerator be 0, you let the what? denominator be 0, right? And what that means is you have 1 minus the natural log of x is 0, and then you have x squared is 0. Now, when x squared is 0, that means x is 0. So, okay, we have a solution there. Natural log x equals 1. You might say, well, how do I solve this? You could do it two ways, right? You can look at that. These are my powers. E to the natural log x, okay, is really going to be x. And that's e to the first power, which is just e. So my point is you have two solutions. However you want to look at this situation, 0, e, well, this is where your first derivative, these are called critical values. Is that true? So at 0, this is the derivative does not exist. Okay, at e, the derivative is what? 0. So I want to just go with the flow on this here. Region 1, region 2, region 3. Okay, so this is looking at the first derivative and its critical values. It's where the derivative equals 0, right? It's where the derivative is not defined. It's sign analysis on that first derivative. But if you're awake, what do you remember about the domain that we pointed out? X is greater than 0. So in other words, there's no sign analysis on region 1 at all. And that's where students might make a mistake. Okay? Because it's not in the domain. So when I go proceed and say, okay, we need some test points, right? E is about 2.718. Is that right? So I can use 2 as a test point, and I can actually use 3 as a test point, so you guys know. Okay, you guys see what I'm saying? And you're testing the first derivative. So if I put a 2 here, you go, okay, I put a 2. My denominator is positive. It's 2 squared. But 1 minus the natural log of 2. What do you guys know about 1 minus ln 2? Is that positive or is that negative? 1 minus ln of 2, we know is going to be what? A nice positive number. Okay, so I'm saying you got positive over a positive. What does that mean? Region 2 is what? Positive. You have an increasing slope. Plug in the test point of now 3. Now I know 3 squared is positive down there, but what is 1 minus the natural log of 3? You go, okay, 1 minus natural log of 3, you see a what? Negative. So in other words, I got a negative over a positive. We know that's what? Negative. So what you guys are seeing here is your answer. This picture is worth what? 1,000 words. In fact, the interval where your function is increasing, ladies and gentlemen, let's find some colors here. Maybe pink. 0 to e. We're increasing. E to infinity, your function's what? Decreasing. So let's write this information down, okay? This is our conclusion here. This is all the observations we can make. The function f is increasing on the interval 0 to e. F is decreasing on e to what? Infinity. Okay. You have a horizontal tangent at what? X equals e. Or what do we really say? This is the location of a what? Are you on top of a hill? Or are you in a valley? top of a hill. Is that right? So that's going to be, really, we say that's a local max. However, what do you guys know? That goes down forever. Doesn't come back up. So it's not just a local max. It's a what? Yep. So F has an absolute max. Where? At F of what? E. Okay. The absolute max equals, has an absolute max at X equals E. The absolute max is F of E. So what was F anyway? Do you guys remember what F was? F was the function natural log of E over E. Or natural log X over X. So we know this is really 1. Your absolute max is 1 over E. So this is kind of the increasing. We'll put pink and then brown. All right. Increasing on that interval. Decreasing on this interval. A picture is worth what? 1,000 words here. Okay? Horizontal tangent. Horizontal tangent. So even, that's where the derivative was 0. So really in this picture, where was that thing that there we go. It's not easy to see in this picture. But at E, and then that other value is 1 over E by any chance, you're actually to the left, you're actually, it's increasing up to that point E, and then it's decreasing forever. So just looking at that curve, But it's actually just what you're really looking at, in all honesty, here, we're doing what? We're doing some calculus. Yes?
When we're finding the absolute max, do we have to convert X to E, or is it okay if we just take the original function?
No, when you really want to give an absolute max, you want to do it the way I showed you here. In other words, you got to evaluate the value at that function. Now, sometimes they put a little shorthand because there's a lot of work or something in something, but for this one, there's not a lot of work at all. So because there's not a lot of work, you just put natural log E over E is 1 over E. You can, but like I said, it depends how the question's worded. Even if they say, "What is the absolute max?" 1 over E. Say, give me the location of the absolute max. Oh, okay. E comma 1 over E, because location is another word for point. Give me the point on that curve. So it actually just depends, really, ironically, on the language. Anyway, how about this? Have you guys tried some just for fun? How about if I ask you guys this question? Determine the intervals of what? Concavity. And you go, well, what is that? You go, y is, here's your function. You gotta be careful. You gotta actually always be careful what you ask. But anyway. So for intervals of concavity, what do you guys always want to remember? Think of the process. What do you have to do? Sign analysis on what? On your second derivative. So we'll give you guys some time. Let's try this out, see what you guys got. All right, let's try these out here. Okay, so ladies and gentlemen, if you're going to get the second derivative, you got to get the first derivative. Is that right? So y prime will be, differentiate what? This function. So what does that give you? Remember, you're going to have to use what here? Nope. Chain rule. This portion here is your u. So you say, well, what is chain rule? Well, it's 1 over the u, but your u is 1 minus x squared, right? That's the u, times the derivative with respect to x of that u. Okay, so this is this is what you want to learn, is this chain rule version of the formula. Okay, so once you have a derivative formula, chain rule is like, oh, they're going to test you on chain rule, So all you really have to do now, what's the derivative of this minus x squared? Is that right? Isn't that minus what? Minus 2x? So it's negative 2x. So this would be negative 2x over, 1 minus x squared. Now that's your first derivative here, ladies and gentlemen. Okay? Okay, you guys okay with that? Now, you need the what? The second derivative. And so the second derivative for you will be, by definition, the second derivative is the derivative of the first derivative. So, you're going to, maybe I would say to you guys, use that property, pull out the negative sign, right? You could do it this way. There's a few ways you can do it, but I would put it, I'd maybe do it this way. You're pulling out the constant, right? So what you want to do now is make sure you what? Here, you're going to use what rule now? Quotient rule, right? So I have to move everything. Square the denominator. Bring your denominator up here. Differentiate your what? Numerator. Minus that numerator, and then you differentiate the denominator. Okay? So here's your chain rule version again. So, I go back again here and I differentiate. Derivative of 2x will be 2. We know the derivative of minus x squared is minus 2x here. So at this point now, second derivative, 1 minus x squared, you got 2 times that 1 minus x squared minus the 2x times a minus 2x. That minus sign. So we get 2 minus 2x squared plus what? What is that? Is that 4x squared, right? You got that minus sign that was already out there. This will be 2. What is that? Is that plus 2x squared? Double check. Don't know who's calling me. I think it's the doctor. Let me double check here. Hello? This is he. Yes. Yes, let me double check, okay? Yes, I have that. Thank you. Bye-bye. Sure enough, was the doctor. Have to confirm. All right, so you got this. Let me do this here for you guys. You see this negative sign that we pulled out? Okay, we can do a couple of things here. I'm gonna put this back in my numerator. So it's negative 2 minus 2x squared here. I'll be 1 minus x squared squared. And I think I can factor out that negative 2. Let me see if that means anything. I get negative 2. Now that's plus x squared, I guess. And no, I thought I was going to be able to do what? Cancel, but I can't cancel here. Okay, we can't cancel, can we? Right, you guys know what I'm saying? We can't do any sort of cancellation on this here. All right. So let's stop and think about this here for a second, right? Sign analysis again. We got a numerator. We set equal to 0. We got a denominator. We set equal to 0. So, say I'm going to do this 1 plus x squared equals 0. And then I have down here 1 minus x squared squared equals 0, right? Numerator is 0, denominator is 0. And then this implies, if I divide both sides by that negative 2, what do you guys notice? X squared is negative 1. I'm going to say a couple of things here. There's a couple of ways I could look at it. I can say this never happens. Is that true? I mean, it happens only for complex numbers, but it never happens for what? Real numbers. So you're throwing that part out in terms of solving this equation because it gives you complex solutions. Okay, that solution will give you complex numbers. However, here, this does happen. We can have what? 1 minus x squared squared equals 0 by the square root formula is 1 minus x squared equals 0. In other words, whatever you have under here, if it's squared and it equals 0, that implies that that number has to be 0. That's the only way that happens. And then even better, we say x squared is 1, and then we know x will be plus or minus 1 now. So that's going to be important in sign analysis. All right? Now, you say, what's the story? Well, this is the second derivative, and this is where that second derivative, let me apologize to you guys, that's not where it equals 0. That's where it's undefined, because that was denominator. Is that right? So region 1, region 2, region 3, okay? So I have to test the regions. However, go back to the function. Never forget this function. What's the domain of this function? I don't know. What's that domain? Yeah, it's going to be from -1 to 1. You go, what are you talking about? Yeah. Remember, this domain, ladies and gentlemen, this will be your domain, okay? I believe that's our domain. Why is that the domain? Anybody know why that's your domain? Well, it's not just okay, natural log, here's what you would really do. If you really wanted to know why that is, and you should. You say, why should I? Because what you're going to end up doing in your sign analysis, you're going to throw out these regions here. You don't test those regions. Region 1's gone. Region 3's gone. In other words, this is gone. It's not even part of your answer at all. This is where people make a mistake. But you might say to me, how do I know that that's my domain? Well, doesn't this input 1 minus x squared has to be what? Greater than 0. Is that true? That portion needs to be greater than 0 for the natural log function to be defined, that input. And if you do sign analysis here, you say, what would that give me for sign analysis? That gives you what we're saying here, just so you guys know. That x has to be between -1 and +1. And you can't equal -1. You can't equal +1. Okay? Because if it was that, it's 0. You can't take natural log of 0. So my point is, you're going to have to do what here? Sign analysis here. And you want that to be positive, that portion to be positive. Okay? So now when you test this, very easily now, you can say, I'm going to use the 0 as a test point. Whenever 0 is available, ladies and gentlemen, use 0. You guys know why that's always a great idea? Why is that always great? Because arithmetic with 0 is the easiest arithmetic you can do. So if I plug in 0 on the second derivative anywhere, right? Plug in 0 here. Plug in 0 here. Do you guys know what you get? Negative over a what? Positive. And what's negative over a positive? So in region 2, guess what, ladies and gentlemen? Region 2, you're what? Negative. What does that mean? That means this function, we can say f is concave down on what? From -1 to +1. It is not concave up anywhere. And there's no inflection points. So that's all that's happening with this curve. It's strictly concave down in that particular region. So you might say, what does Desmos say about this curve, okay? Well, you got, what is this again? Y equals natural log of 1 minus x squared. This is Desmos. This is the curve they're talking about. Natural log of 1 minus x squared. It kind of resembles the curve, just so you guys know. It really resembles the curve y equals what? 1 minus x squared a lot. Okay, that inside function, right? But the natural log acting on it really makes it what? You have -1 and +1. You have these things called vertical asymptotes. The curve never crosses -1 and +1. You know, but without the natural log, it actually it behaves like 1 minus x squared. You know, so just want to kind of let you guys know that that's kind of a good example here. Anyway, good things. And then, generally speaking, let me do this. If we can get it in, I hope we could get it in. Remember we did the change of base yesterday, right? I'm going to give you a fact about how to differentiate log functions in general, right? Because we looked at a particular log function. Well, from yesterday, and I put it in, purple. Remember log base b of x? What was that? Wasn't that natural log of x divided by what? Natural log of b? That number is a constant down there. And I guess I actually kind of like putting my constants gray. Okay? So if you said to me, well, what's the derivative in general here? Well, let's see. If I differentiate what? Log b of x, isn't that the derivative of what? Ln x over that constant, ln b? And what do you do with the constant? We get to pull it out, right? Natural log of b, that's a constant. And then you just differentiate what? Natural log of x. You know what that is? We already have a formula for that. It's 1 over x. So, the fact I want to give you is the derivative is just going to be what? It's going to be a multiple, well, put the x down here. And that's like the derivative of any what? Natural log. So for example, a very simple example would be if they said, can you differentiate just log of x? Very simple question. So what is the base here? Do you guys know? 10. So you say, is that going to be 1 over the natural log of 10 times x? And the answer is what? Yes. Okay. And then you say, is there a chain rule version? Sure. Once you get a derivative formula, you always get chain rule free of charge. But this is now going to be u is a function of x. So you say, what is that? Well, it's the same, 1 over natural log b of u, but the chain portion is to say du dx. Okay, you got that chain rule version here. And then another quick fact, just so that we can check these boxes. Right? What if you have to differentiate just an arbitrary exponential function? Okay. Well, you're going to say, okay, y here is b to the x, okay? And I'm going to replace this b to the x here. This you can't really see coming. Y is b to the x. So you replace this here with what? E ln b. There's your b. That's to the x. So what I'm really saying, if I can kind of find the color, maybe pink. B is replaced with E ln of b. Those are equivalent. And so if you differentiate the left, you get to differentiate the right, which is just E ln b x, which is E ln b x times the derivative of that ln b x. And we know what that is. That's going to be the constant ln b. And then this thing you put back. Say, was that b? Yeah, that was b. Say, is that just b to the x? Natural log b, and it is. But it's a constant. So you can say, oh, that's just going to be what? The value natural log b now times b to the x. So this is how you differentiate an arbitrary exponential function. Not the, you say not what? Not the exponential function. Anyway, and then you go, what is this here? Once you have this, yes, I can give you a chain rule version, but I'm going to give you the, from this, once you have this, what does that mean? It means the integral of natural log b to the x dx is b to the x plus c, which means the integral of b to the x dx, if I pull out my constant, because this is a constant, right? And I divide both sides by that constant, maybe you want to see every detail. Right, so you say, can you pull out the constant? And you just have the integral of b to the x dx. I'll say yes. Well, divide both sides by the constant, and you get a nice integration formula for b to the x. That'll be b to the x over natural log b plus, you can say d, if you say what's c divided by natural log b, d whatever. Okay, so you get a nice integral formula from that. So, I mean, it's something kind of simple in a way where if they ask you to integrate maybe 10 to the x, let's do 10 to the x. Well, it'll be what? 10 to the x, natural log of 10 plus that c, for example, you know. And of course, you could do a u sub, but I don't think the book gives you questions on a u sub on that, in all honesty. You know, I think the book kind of stops right there with some of these kind of examples. But did we do the log? I think I did do a log example. Did I do a log example base 10? Yeah. You know. Anyway. All right. What are we looking at here online? Let's double check here, ladies and gentlemen, everything here. So for homework 1, notice we have limits of logs. And then you're going to have, some of these questions are from like 7.4, in case you guys didn't know. And I'll double check exactly 7.4 of the book. I don't, okay, do I have it in front? Yeah, we got a little bit of time. Just go to the table of contents since I'm looking at it now. Yeah, derivatives of log functions. This is derivative of exponential functions. So if I edit this here, it's really calculus. And the 7.2 is derivative of exponentials. So it actually makes a lot of sense. And yeah, I think it makes a lot of sense. So anyway, and then what's 7.5 exactly going to be? We're not there yet. We're still at derivatives of log functions. Inverse trig functions. Okay. The titles are kind of odd. Okay, so just to kind of fill in the gaps so that we know what we're looking at. So we're kind of looking at some of those things. Derivative of log functions. We're not done because tomorrow we're going to do some do a process known as logarithmic differentiation, and they're going to do some integration of integration. So we still got a little more differentiation from the section and integration. A big part is also integration from this section, I think. Let me double check. We got some, but that's coming up. So I just wanted to label that for you guys, okay? All right, we're out of time. So what do you guys think? Does that clear out some cobwebs with some of these things? I hope. All right, okay, well, we'll see you guys later. Take care. Have a good day.